Hello there and welcome back to the Science Sleepy Minds. Tonight, you're floating weightless, suspended in a void so immense it laughs at your concept of distance. All around there is nothing, until there's everything. A monstrous curve in the cosmos ahead of you, a region where even light stops trying. The stars thin out. The laws of physics begin to chew on their own fingers. You're approaching a black hole, a supermassive one, the kind that squats at the center of galaxies and swallows suns like breath mints. Its event horizon yawns before you, a perfect sphere of nope. There's no surface, no bottom, just an invisible border beyond which the universe turns its back. You're close enough now to feel time stretch. Seconds bleed into minutes, minutes lose all meaning. Light from stars behind you bends unnaturally around the black hole's edge, forming a glowing halo. The gravitational lensing effect, elegant and creepy, like a cosmic mood ring. You're about to learn something truly humbling. Light can escape from black holes, just not from the inside, and not in the way you might expect. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and local time in the comments. I love seeing where and when you're listening from. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You hover just outside the event horizon, where reality frays at the edges. You can't hear anything, space is silent, but if you could, you'd catch the hiss and crackle of radiation from an accretion disk. Matter, swirling like whipped cream at relativistic speeds, superheats and screams in X-rays. This is the black hole's buffet, stars shredded, gas clouds pulverized, all funneled into a spinning disk tighter than a DJ's playlist. The friction alone is enough to light up the galaxy. Black holes don't actively pull things like cosmic vacuum cleaners. Instead, they're just extremely persuasive. Gravity here is geometry. Space itself dips so sharply into the hole that falling in becomes the most natural thing in the universe. You, drifting closer, start to feel it in your atoms. If your feet were closer to the horizon than your head, you'd get stretched. That's spaghettification, yes, a real term, and you'd become a long, sad noodle of yourself. Luckily, you're observing from a safe enough distance, for now. Here's the wild part. Despite being the ultimate sinkhole, black holes can shine brighter than anything in the cosmos. The secret is not in the hole itself, but in what almost falls in. Not everything spiraling down makes it across the event horizon. Some of that matter and energy gets redirected, twisted by magnetic fields and spat out from the poles at nearly the speed of light. These are black hole jets, and they're not just bright, they're absurdly bright. Imagine a flashlight powerful enough to outshine an entire galaxy, and then realize it's coming from a region smaller than your solar system. Historians still argue whether the first hints of such jets came from the optical oddities of early radio galaxies, or the suspiciously linear emission in distant quasars, but one thing's clear. Astronomers didn't expect light to come out of a black hole's neighborhood. That's like finding a disco ball in a cave. You float a little higher now, watching plasma whip in curved arcs like paint flung from a brush. It's chaos, but there's form. The innermost regions of the accretion disk twist into tight spirals, heating to billions of degrees. Magnetic fields, generated by the sheer violence of motion, begin to coil and snap upward along the black hole's rotational axis. That's where the jets form, perpendicular to the disk, like beams from an invisible lighthouse. And these aren't gentle breezes. Black hole jets are focused streams of plasma, radiation, and magnetic fury. They travel thousands of light years, punching through interstellar space with the delicate grace of a sledgehammer. Some jets last a few thousand years, others stay lit for millions. The biggest ones sculpt entire galaxies, carving cavities in hot gas, compressing matter, halting star formation, or triggering it. You blink. Wait, no, you try to blink. Time is acting weird again. You're close to what's called the photon sphere, a region where light orbits the black hole. Not falls in, not escapes. Orbits. If you released a flashlight sideways from this distance, the beam would go around the black hole in perfect circles. You could, in theory, see the back of your own head if you stood still long enough. It's beautiful, terrifying, utterly unnatural, and yet totally real. Let's break that for a moment with something strange. Some ancient texts, especially in medieval Islamic astronomy, contain remarkably poetic descriptions of dark stars, objects so dense light could not escape. Coincidence? Maybe, but you have to love when centuries-old speculation brushes against modern astrophysics. Now you're watching a newborn jet form. The accretion disk flares suddenly. Something big just fell in. A star? A gas cloud? Who knows? The magnetic fields intensify. Charged particles are flung upward, following those field lines, and then, bam! A jet ignites. It isn't smooth. It jitters, pulses, and then stabilizes, a beam of pure fury stabbing out into the void. It's so bright it would blind you if you still had eyes. Here's the kicker. This jet didn't come from inside the black hole. It's powered by the extreme environment around the event horizon, by the matter that never quite made it in. Kind of like how steam hisses out of a kettle spout, but never from the water inside the kettle's walls. And yet, this process might not be universal. Some black holes jet, others don't. Some burp out tiny flickers, others unleash continent-sized beams for epochs. Astrophysicists still don't agree on what flips the switch. Is it the spin of the black hole? The density of the accretion disk? The cosmic mood? The debate is ongoing and vicious, in a very polite, peer-reviewed sort of way. But you're just a sleepy little observer, drifting through time-dilated chaos, watching the universe play with its most powerful toy. You drift backward, gently now, away from the gaping event horizon and into the cosmic neighborhood surrounding it. The jet blazes behind you like a divine sword, a beam of fury from a hole in space-time. But out here in the galactic outskirts, things get quieter and messier. This isn't a pristine vacuum. This is the playground of gravity, the not-so-empty space where black holes feed. It's easy to imagine space as cold and dead between stars, but your eyes adjust to the unseen. Here lies the interstellar medium, gas clouds, dust lanes, wandering rogue stars, entire stellar nurseries, all loosely bound in a chaotic ballet around a supermassive anchor. You coast past tendrils of ionized hydrogen, glowing faintly pink if you could shift your vision to just the right wavelength. A faint scent of ozone would hit your nose, if noses worked in space. But the silence is dense with implied violence. Galaxies, you realize, are not smooth systems. They're turbulent cities of matter, and black holes are their unruly landlords. You spot stars arcing in bizarre orbits, shaped not by the mass of the stars alone, but by a gravitational heavyweight hidden in plain sight, the central black hole. This region, called the galactic bulge, is thicker with stars, some older than Earth's crust. Every one of them is moving. Some are doomed. You pass over a dust ring, it's thick, shaggy and cold, until you look beneath it. That's the accretion disk's outer neighborhood, where things begin to heat. It's like watching smoke curl off a simmering pot, and you're just starting to see how the whole process begins. Matter falls inward slowly at first. It's friction and density that wake it up, like a fire stoked from the edges, and not all of this matter falls freely. You see blobs of gas held in place by the opposing tensions of gravity and angular momentum. They hover, waiting for a nudge, a supernova shockwave perhaps, or the chaotic collision with another gas stream. Once disturbed, they'll spiral inward, heating up until they glow in ultraviolet or X-rays, feeding the accretion disk like an IV drip into the maw. One of the weirdest things you notice is how organized the chaos becomes near the black hole. Farther out, you see dust clouds shredding themselves in slow motion, tangled into ribbons by gravitational tides. But as you approach the inner regions, all that matter starts aligning into a disk, a violently flat one. It's a consequence of angular momentum conservation, the same physics that keeps pizza dough spinning evenly when tossed. Only here, the dough is a few 100 million degrees, and you are very much the pepperoni. It's also here, in this turbulent outer ring, where you stumble across a historical oddity. In the early 20th century, astronomers mistook some of these luminous galactic cores for stars and gave them the name quasi-stellar objects, or quasars. It wasn't until radio telescopes came along that we realized, those aren't stars. They're entire galaxies with engines powered by black holes flinging jets of plasma at light speed. Whoops, easy mistake. Speaking of those jets, they're not firing at random. You begin to notice a pattern. The jets seem to align with the rotational axis of the black hole, and that axis? It's defined by the structure of the accretion disk itself. So in some beautiful, brutal irony, the very material trying to fall in is what guides the light escaping out. Think of it like a blender where the liquid is trying to crawl out through the lid while spinning it faster. Still, not everything makes it to the centre. Some matter hits traffic jams. You watch two gas clouds collide, compress, and collapse into a quick starburst, a tiny batch of new stars born in the chaos. This is the AGN torus, a donut-shaped structure of dense gas and dust surrounding the active galactic nucleus. It sometimes hides the black hole entirely from view in visible light. Imagine trying to see a flashlight through a fog of soot. The light is there, you just need the right eyes. Now, just for flavour, here's a fringe theory that still gets murmured at conferences over burnt coffee. Some scientists speculate that galactic collisions, or even flybys, can wake up dormant black holes, nudging nearby matter into a feeding frenzy that sparks accretion disks and, if conditions are just right, launches jets. In other words, you might get blasted with a light-speed plasma beam, not because your galaxy did anything wrong, but because it bumped into someone bigger on its way home. Galactic road rage, basically. You rotate slowly, peering around at the larger context. That dust! It's a remnant of ancient supernovae, the gas, possibly exhaled from red giants, or sneezed out by Wolf-Rayet stars before they went boom. It's like the black hole is being fed leftovers from a billion years of stellar drama. It doesn't need to hunt, it just waits, and you, lucky traveller, get to watch the prep work before the jet ignites. This is the backstage, the kitchen, the messy, sticky, glowing place where light is born not from within the black hole, but from its appetite. Historians still debate whether the first clear images of accretion disks and surrounding matter came from Chandra, Hubble, or earlier radio interferometry. But what's certain is that we didn't grasp the scale of these cosmic kitchens until we could see in X-ray, infrared, and beyond. Now we're aware that this not-so-empty space around a black hole is arguably the most dynamic region in the universe. A few faint pings echo from your long-range awareness, gravitational waves. Somewhere far away, two black holes have merged, shaking the fabric of reality itself. The idea that these events can stir up the surrounding medium, trigger feeding events, and even wake up old jets. Not confirmed, not disproven. Like much in black hole science, it lives in that foggy borderland between awe and uncertainty. For now, you float quietly, eyeing the whirling, whispering edge of an engine built to annihilate information, and somehow it glows. Now that you've lingered among the dust clouds and gravitational swirlies of the galactic core, it's time to spiral in closer to where the real action happens. Welcome to the accretion ballet, the swirling, shrieking disk of matter so hot and so fast that even subatomic particles get dizzy. You're about to dance along the razor-thin edge of destruction, where matter pirouettes toward oblivion, and light becomes a side effect of suffering. Picture this. You're hovering just above the accretion disk, maybe a few thousand kilometers from the event horizon of a black hole the size of several million suns. Below you, matter screams past at a significant fraction of the speed of light. There's no sound, of course, but your mind fills in the hissing, growling roar, like standing beside a jet engine made of plasma and heartbreak. The disk isn't smooth, it flickers, warps, and pulses with heat. Huge chunks of ionized gas twist in, collide, and shear apart. Electrons strip from nuclei, magnetic fields tangle like spaghetti, and photons are flung out like confetti. You're looking at the brightest process the universe can manage, short of the Big Bang itself. That's because friction and gravity are locked in a perpetual wrestling match down here, and friction is winning the early rounds. As you drift across this storm, light flashes from iron atoms being torn apart, giving off characteristic X-rays. If you could see in X-ray vision right now, the view would be blinding, but not uniform. You'd see hotter, denser rings closer to the black hole's edge, whipping around at incredible speeds, while the outer disk moves more sluggishly, like syrup drained into a spiral. The accretion disk isn't a flat, happy pancake either. It wobbles, it warps. Sometimes it even tears depending on how the black hole spins. That's called lens-thirring precession, and it's caused by the frame-dragging effect of a rotating black hole twisting spacetime itself. Yes, you heard that right. Spacetime gets dragged around like an old hoodie tied around a spinning teenager. It's wild, and it's real. Here's a mainstream historical gem for you. The theory that black holes could have accretion disks glowing in X-rays was first proposed seriously in the 1970s, following observations of Cygnus X1, one of the first strong black hole candidates. The X-ray emissions didn't make sense unless something very, very hot was spiraling into a compact invisible object. The idea of a dead star with a feeding disk started to catch on. Turns out dead stars are messy eaters. Now focus on the jet's origin point. You're hovering above the poles of the black hole, where the accretion disk tapers off and magnetic field lines begin to rise like twisted ropes of invisible lightning. You can almost see the beginnings of the jet forming, charged particles lining up along the magnetic poles like marathon runners at the starting line. Some of that matter will plunge into the black hole, but a select few, lucky, unlucky, depending on your viewpoint, get launched upward and outward, accelerated by a mix of magnetism and sheer gravitational fury. Still, don't jump ahead to the jet yet. Stay here. Watch how the disk feeds the beast. It's not a perfect inpour. Matter stalls, eddies, and occasionally surges, causing the disk to brighten or dim unpredictably. This variability, this flickering, is how astronomers study these systems from Earth. Light curves and spectroscopic wobbles become the breadcrumbs we use to map this invisible madness. And sometimes the black hole takes a bigger bite than expected. You've probably heard the term tidal disruption event. It's when a star gets a little too close, and instead of a gentle snack, the black hole tears it into glowing shreds. The remains form a temporary accretion disk, sometimes resulting in a short-lived but spectacular jet. It's basically the universe's version of an impromptu barbecue. Let's throw in a quirky tidbit. Back in the early 2000s, some researchers proposed that weird changes in accretion disks might be influenced by orbiting planets or planetary debris getting too close. Imagine, a forgotten gas giant gets nudged in, starts to spiral toward doom, and temporarily alters the whole disk structure. It's not widely accepted, but it's fun to imagine the ghost of a planet haunting a black hole's dinner plate. You can now see the inner edge of the disk, the innermost stable circular orbit, or ISCO. Any closer, and matter can't hang on. It slides in, and that's that. For a non-spinning black hole, the ISCO lies at 3 times the Schwarzschild radius. But for a rapidly spinning one, the ISCO gets pulled in closer, meaning the disk can reach deeper into the gravitational well, get hotter, and radiate more furiously. That's why spin matters. It changes everything. Historians still argue whether we fully understand the viscosity in these disks, what exactly causes them to lose angular momentum and fall inward. The prevailing idea is magneto-rotational instability, where tiny magnetic irregularities snowball into huge frictional effects. But no one's seen it directly. Like so much in astrophysics, it's inferred, modelled, and fiercely debated in PDF-laden email threads. You pass above a dense clump in the disk, likely the remnants of a shattered asteroid or mini-planetesimal pulled in from the outer system. It's glowing unevenly, tumbling chaotically, throwing shadows in the X-ray like a bat in a strobe light. This is a chaotic place, but not random. There are rules, horribly unfair rules, but still, rules. As you watch this ballet of destruction, it's hard not to feel a little sympathy for the particles below. Each one is just following the curve of space-time. They fall, they crash, they heat, and then, maybe, they get launched as part of something bigger. A jet, a beam of light from the darkest place, but not yet. First they must swirl. You've spent enough time on the edge of the whirlpool, now it's time to get personal, very personal. Brace yourself, because you're about to take the plunge into one of the most unsettling processes in all of astrophysics. Spaghettification. Yes, that's the actual term. It sounds ridiculous. It is ridiculous, but it's also terrifying. As you begin your descent toward the event horizon, the rules you've relied on, distance, time, mass, sanity, begin to unravel just like your atoms will if you get much closer. You don't fall straight in, not yet. You're still coasting along the accretion disks in a rim, where every millisecond brings you closer to the point of no return. Already you can feel the gradient of gravity increasing beneath you. That's the key to spaghettification. Not the strength of gravity itself, but how rapidly it changes across the length of your body. Your head and feet experience different accelerations. You stretch. If you were made of anything solid, you'd feel it immediately. Your body elongating, atoms pulling apart, molecular bonds groaning under the tidal stress. But you're more idea than flesh in this journey, so you get to hover and observe. Still, your mind reels at what this place does to matter. Let's make it visceral. Imagine standing over a waterfall, except this waterfall is made of curved space-time, and instead of water, its entire coordinate system's crashing down. Time dilates as you move inward. From an outside perspective, you slow to a crawl, frozen just above the horizon. But from your point of view, you're still moving, down, forward, in, faster and faster. As the universe stretches vertically and crushes laterally around you, you pass the innermost stable circular orbit. Below you, there's no such thing as a safe path. Any matter here is doomed to fall. You're watching particles plunge in, glowing briefly as they cross the final threshold, then vanishing as if they'd never existed. No light returns, no information escapes. It's like reality has an undo button and just hit it. But here's the twist. You're still not in the jet. Not yet. You glance upward. Above the disk, the region begins to thin. Sparse particles, charged and dizzy, spiral upward along invisible threads. These are the very early seeds of a jet, but you're still deep inside the turbulent nursery of destruction. Nearby, a small black hole, stellar mass this time, passes within your field of view, dragging along a companion star. The star is in big trouble. Its outer layers are being siphoned off, pulled into a tight accretion stream like honey from a broken comb. A fraction of this in falling matter starts coiling around magnetic field lines, pulled away from the disk before it can fall in. You watch as the black hole briefly flares. A baby jet flickers out of its pole, thin, stuttering but undeniably real. Even little black holes want to shine, apparently. Fun fact, the term spaghettification wasn't coined in some dusty research paper. It came from British astrophysicist Sir Martin Rees in the 1980s, who had the good sense to describe gravitational tidal forces in language that would stick. And it stuck. To this day, it remains one of the few physics terms that sounds like it belongs on a diner menu in a gravestone. You rotate slowly, watching the vertical column of the black hole's magnetic axis. The accretion disk looks impossibly thin now, thinner than a CD edge but hundreds of thousands of kilometers wide. Matter is falling in like moths into a blender. Meanwhile, just above the poles, the jet region is clearing. This is where things get weird. Magnetic field lines begin to dominate over gravity. Yes, really. While gravity still wins near the event horizon, those magnetic fields, twisted by the spinning disk, begin to channel energy upward. You pass through a ghostly corkscrew of charged particles. They're accelerating, heating, changing direction so fast you can barely track them. Historians still argue whether the first confirmed detection of spaghettification happened in the observation of a star shredded by black hole J2150-0-0551 or a few earlier events masked by noise. What's clear is that the process isn't just a textbook oddity. It happens. It happens violently and often. You fly upward a bit to avoid becoming a cosmic noodle, passing through a region called the ergosphere, if you're dealing with a spinning black hole, that is. Here, space-time is being dragged along with the black hole's rotation. Nothing can stay still. Even light gets carried along like a tourist in a rip current. But unlike the event horizon, you can still escape the ergosphere, if you're clever or extremely lucky. This is where energy extraction might happen. The Penrose process? Anyone. In theory, you can toss something into this region, split it in two, and steal energy from the black hole's spin. And yes, some scientists believe this is part of what powers the jet. The black hole doesn't just allow light to escape, it might actually help fling it out, using its own rotational energy. The jet isn't just a plume of particles, it's a finely tuned structure of violence. You glance upward and see it forming now, faint lines sharpening, plasma aligning, radio waves beginning to hum. The jet isn't born all at once, it bubbles, builds, and then it erupts. But only if the conditions are right. Here's a fringe theory just to spice things up. Some physicists have argued that if you could somehow survive the plunge through a supermassive black hole, and if it were connected to a white hole, theoretical of course, you might emerge somewhere else in space-time. Maybe another universe, maybe the past, maybe Cleveland. But that's assuming you survive spaghettification, tidal forces, quantum evaporation, and being compressed into a dimensionless point. So, probably not. Still, in this region, this warped stretched zone where the jet hasn't quite formed but is about to, you're watching the last dance of matter. these particles won't be seen again. They'll become light, or radiation, or whispers on a radio telescope thousands of years from now. You take one last look down into the hole. It stares back, unblinking, infinite, unknowable. Then you turn your gaze upward, where light is beginning to break free. You're not out of the darkness yet, but for the first time you see the way through it. Upward now. You rise along the rotational axis of the black hole, out of the twisted chaos of the accretion disk and into a column of space that feels oddly focused. Not calm, definitely not calm, but organized. This is where the jet starts to sharpen into existence, and the culprit behind this cosmic laser light show? Magnetic mayhem. If you've ever played with magnets as a kid, and marveled at how iron filings arrange themselves into neat patterns, congratulations, you've already grasped 1% of what's happening here. The rest? Utter madness. Magnetic fields near a black hole aren't static lines like the ones sticking your grocery list to the fridge. They're three-dimensional, dynamic, and twisted into obscene spirals by the spinning fury of the accretion disk. You pass through loops of invisible energy. These fields are generated by the motion of ionized gas in the disk, charged particles whipping around at relativistic speeds, creating currents, which in turn spawn magnetic fields. These fields don't sit idle. They get stretched, sheared, and flung upward along the black hole's spin axis. It's like the black hole is braiding electromagnetic ropes and then yanking on them with everything it's got. Here's where things get extra dramatic. Those magnetic field lines, all tangled up like a bunch of electrical extension cords left too close to a toddler, start to reconnect. Reconnection is when magnetic field lines snap and rejoin in new configurations, releasing a colossal burst of energy. You might have seen this with solar flares on the sun. Now imagine that, but with gravitational steroids and a near light speed twist. That's the energy surge that helps launch the jet. Remember how close you were to the event horizon? Good. Because right now, some of the jet's energy may be coming directly from that region. The Blandford-Zenarjek process, yes, it's a mouthful, theorizes that if the black hole is spinning fast enough, it can transfer energy to the jet via magnetic field lines anchored near the event horizon. Think of it as tapping a cosmic flywheel and using its momentum to power a spotlight that crosses galaxies. Historians still argue whether this process dominates over the simpler Blandford-Payne mechanism, which taps energy from the accretion disk's rotation instead of the black hole's spin. The truth? We don't know for sure. It might be both. It might be neither. Jet formation is still one of the most hotly debated puzzles in high-energy astrophysics. So, if you want a guaranteed Nobel Prize, maybe figure it out. You've got time. You're a floating consciousness near a black hole after all. As you glide higher along the axis, you notice something strange. The space around you is empty, but not quiet. Particles are being accelerated here. Some are electrons and positrons, antimatter. Others are protons and heavier nuclei. They're all being funneled into a tightly collimated stream, guided by those magnetic field lines you passed through earlier. The farther out you go, the narrower the beam becomes. And here's your quirky fact of the night. Astrophysicists have noted that some black hole jets appear to wobble, like a spinning top just before it falls over. This precession may be caused by the black hole interacting with another black hole, or the warping of the accretion disk. One fun theory, a misaligned spin axis, like a drunk black hole trying to figure out which way is up. You see it in the shape of the magnetic fields too. They aren't perfectly straight. They corkscrew. The jet, therefore, corkscrews, which means if you're an unfortunate galaxy sitting downstream from that twisting beam, you might get periodically flash-fried every few thousand years. A slow-cooked cosmic rotisserie, if you will. Farther still, you sense an increase in velocity. The particles in this jet are being accelerated by magnetohydrodynamic forces. That's just a fancy way of saying electromagnetism plus fluid dynamics. But in space and on fire, the speeds are incredible. Near the base of the jet, matter is already hitting 90 to 99% the speed of light. The term for this is relativistic jet, and yes, that means time slows down for anything riding it. If you boarded this beam and rode it straight out, your internal clock would tick slower compared to the rest of the universe. This leads us to another strange truth. These jets are invisible in most light. The base of the jet glows in X-ray and gamma ray. Farther out, as it hits surrounding material, it begins to emit in radio waves. It's only when those shock waves interact with clouds of dust or intergalactic gas that we start to see the results. vast lobes of glowing radio emission, sometimes larger than the entire galaxy that birthed them. But right now, you're still in the launch corridor. It's tight, narrow, lethal. The environment is thick with energy and raw electromagnetic fury. And in this narrow corridor, something unexpected is happening. Light is escaping, and let's pause on that. Light escaping from near a black hole. It's not coming from inside. That would break physics, and physics already has enough therapy bills. But what's happening is that matter, and the energy it carries, is being diverted before it crosses the event horizon. It's being caught, twisted, funneled, and fired. And the light that comes from it? That's synchrotron radiation, produced when charged particles spiral at near-light speed along magnetic fields. That's your cosmic spotlight, that's the jet. Historians still marvel at the discovery of these phenomena. It was the study of active galactic nuclei in the 1960s that began to reveal just how powerful these jets could be. The first detailed radio maps of galaxies like Cygnus A and Centaurus A showed enormous symmetrical lobes, far outside the galaxies themselves, and the only logical explanation? Jets. Long, violent, sustained ones. You pass through the zone where collimation locks in, the beam now fully formed, its edges sharp as a laser pointer. If you squint, you can almost see the boundary between order and chaos. One side, turbulent disk, broken matter, warped space-time. The other, streamlined radiation rocketing out into eternity. And just for flavour, there's a fringe hypothesis that some black hole jets might contain exotic particles. Dark matter components, perhaps. Some researchers wonder if these extreme environments could be natural particle accelerators, even creating conditions similar to the Big Bang. We haven't detected anything like that yet, but jets do throw cosmic rays at us. Particles so energetic they've been travelling for millions of years only to smack into Earth's atmosphere like intergalactic darts. Thanks, black holes. Really appreciate that. For now, you float just above the point where the jet transitions from chaos to direction. You've made it through the magnetic furnace. You're about to ride the beam. Next stop, relativistic speeds. You feel it before you see it. The sensation of acceleration, of space itself compressing in front of you and stretching behind, as though someone has reached into reality and twisted the fast-forward dial. You are now riding the beam, not metaphorically, not symbolically, literally gliding along the axis of a black hole jet, accelerating to relativistic speeds, and it's strange. The laws of physics haven't gone anywhere, but they're acting funny. Time, for one, is misbehaving. If you were made of matter and had a wristwatch, it would tick slower compared to the clocks back at Earth. The faster you go, the more time bends around you. 1,000 years could pass outside while you experience minutes. Relativity. It's not just a theory, it's your new travel companion. Around you, the jet stabilizes into a beam of highly collimated plasma. Charged particles, primarily electrons and positrons, are spiraling along magnetic field lines at just shy of light speed. You're in a superhighway of radiation, flying alongside energy so fierce that it could melt atoms if you weren't, just consciousness at this point. This isn't an even stream though. The jet pulses, flares and shifts ever so slightly. Think of it like a fire hose made of laser light and hot plasma. Impressive, unstoppable, and very bad news if pointed at your neighbourhood. You look back, way back, and can still barely make out the tiny black speck that is the black hole. From here, the accretion disk is just a faint golden glow, and the twin jets are narrow blue-white beams slicing through space. It's humbling, isn't it? Something that crushes everything in its path also manages to create the brightest, straightest structures in the observable universe. Now let's add some visual candy. The particles surrounding you emit synchrotron radiation, light created by their spiral motion in the magnetic field. This radiation spans from radio waves to X-rays, and sometimes even gamma rays. It's directional too, beamed, which means you get that bizarre phenomenon known as Doppler boosting, where emissions in your direction are brighter, hotter, and more energetic than those behind. It's like turning up the brightness on a cosmic flashlight without changing the batteries. You coast further out, past where the jet is still confined by internal magnetic forces. This is the collimation zone, essentially the black hole's focusing lens. It's a few light years long, depending on the black hole's mass and spin. But now you're entering what astrophysicists call the propagation zone. The jet has fully formed and begun its long trek through interstellar space. Here's a mainstream historical fact. The galaxy M87, which you'll get better acquainted with later, was one of the first where astronomers saw a visible jet in optical light. Photographed as early as 1918, it was a mystery for decades, just a strange linear feature poking out of a galaxy. We didn't know what it was until we learned about black holes and their flashy side projects. Out here, things get weird in a different way. The jet's speed approaches the limit of causality. You're travelling so close to the speed of light that causality itself, the order in which things happen, starts to blur. Events ahead of you take longer to reach you. Light behind you struggles to catch up. Time slows. Space stretches. You're not just seeing the universe differently, you're moving through it differently. You fly past pockets of denser material, gas clouds, interstellar dust, and when the jet slams into them, it creates shock fronts. These are places where the jet's energy is suddenly and violently transferred to the surrounding space, and this, dear dreamer, is where the fireworks really begin. Gamma-ray bursts, X-ray flares, radio lobes. This is the part of the jet we can see from Earth, even across billions of light years. And sometimes, if we're unlucky, or lucky depending on your sense of drama, those jets are aimed right at us. That's called a blazar. But let's not get ahead of ourselves. Right now, you're still skimming the jet's central channel, watching particles accelerate and decelerate in chaotic harmony. Here's a quirky tidbit to enjoy at near light speed. The term relativistic jet wasn't widely used until the 1970s, despite earlier observations of radio sources that hinted at something more dramatic. For a while, scientists thought these might be ejected stars or gravitational outflows. The idea of a black hole spitting light was too counterintuitive. The term only stuck after we realized that these weren't just radio lobes, they were connected to invisible engines. Speaking of engines, let's touch on that open scholarly wound. How exactly do these jets stay so focused for so long? Historians and physicists still argue whether it's purely magnetic confinement, internal pressure balancing against external gas, or some unholy combination of spin, disk chaos, and interstellar weather. We've modelled it, simulated it, argued about it. No single theory quite wins. You fly farther, watching the jet's profile widen slightly, subtly, like the afterburner on some cosmic spacecraft. And even here, light continues to pour from the stream, but it's not the light you're used to. This stuff is non-thermal, born not from heat but from motion and magnetism. If regular starlight is a candle, this is an arc welder. Blinding, focused, intense. Particles begin to diverge slightly at this stage. Some fall out of alignment, crashing into dust and glowing as they die. Others keep moving, destined to travel thousands, millions of light years before finally coming to rest. Some of those particles will smack into Earth's atmosphere as cosmic rays. Others will end up trapped in magnetic fields of nearby galaxies. A few will keep going forever. You notice too that the jet is not symmetric. There's a visible jet, the one you're riding, and a counter-jet on the opposite side. But in many observations we can only see one. Why? Doppler beaming. The jet moving toward us appears much brighter than the one heading away. It's not that one jet's better, it's just moving more in our face. Typical. And now, at last, you begin to slow. The jet is widening, losing focus. You're far from the black hole now, hundreds of light years. The light is dimmer, softer, more diffused, but still fast, still high energy. You've ridden the beam from origin to expansion, and somehow you're still intact. You take a moment to look back. The black hole is gone, swallowed by the distance and the distortion of space. All that remains is a faint line of fury stretching across the stars, a jet, a wound, a message. Light has escaped the darkest place in the universe, and you rode it all the way out. You coast through space now, no longer at the mercy of the black hole's brutal gravity, but still streaking along with the remnants of its light-speed tantrum. The beam has widened slightly, cooled a little, and scattered its particles in playful spirals, yet you're still riding what is essentially a cosmic bullet, and now it's time to fully appreciate just how ridiculous this whole thing really is. Welcome to the relativistic show-off phase. Because when you're moving this close to the speed of light, like 99.999%, everything goes sideways. Quite literally. Time slows, mass increases, distances contract. You're living in Einstein's fever dream now. You look ahead. The space in front of you seems to squeeze inward, stars clustering unnaturally. Behind you, everything stretches, wavelengths of light, space itself, until galaxies blur into microwave whispers. This is relativistic beaming at its flashiest. Light emitted by particles in the jet is no longer evenly spread in all directions. Instead, it's squashed forward into a narrow cone of fury. If this jet is aimed at a telescope back on Earth, it looks insanely bright, sometimes outshining the entire galaxy it comes from, all thanks to your good friend, special relativity. And speaking of Earth, if you were somehow able to send a message back right now, it would arrive long after anyone who knew you had turned into dust. Time dilation is playing games with your future. While only minutes might pass for you on this ride, centuries, thousands of years tick by elsewhere. That's why riding a relativistic jet is a bad idea for long-term relationships. Let's add a little historical flavour here. In the early days of radio astronomy, the 1950s and 60s, scientists started detecting incredibly strong radio sources that seemed to come from small, point-like spots in the sky. They were labelled quasars, short for quasi-stellar radio sources. Everyone thought they were stars. They weren't. They were galaxies with jets aimed directly at us, and those jets were lighting up the sky with relativistic beamed radiation. A case of mistaken identity that eventually redefined our understanding of the universe. You catch a glimpse of one of these brilliant monsters as you pass it. A quasar, many billions of light years away, its jet pointed straight at you. It flashes across your field of view like a divine headlight, blinding in ultraviolet and X-rays. You feel a twinge of respect and mild existential dread. These things are too bright. A single jet can pour out more energy than every star in its host galaxy combined, and it's coming from a region smaller than our solar system. As you glide farther from the black hole's immediate influence, you begin to see the consequences of this beamed energy. Pockets of interstellar and even intergalactic space are being transformed. Clouds of gas that had drifted for eons are suddenly ionized, shocked into activity by the relentless force of the jet's passage. In some cases, jets like this compress gas enough to spark star formation. In others, they scatter it so thoroughly that future stars are forever denied. And still, you're moving. The beam carries you. The magnetic field lines begin to loosen, unraveling into wide loops as the jet interacts with surrounding medium. This is the point where the jet can no longer hold itself tight. It's beginning to transition into a lobe, a broad, glowing bubble of radio emission created as particles slam into whatever stands in their way. You're entering the aftermath of the show. Now here's a fun little detail. Some scientists have found evidence of superluminal motion in jets, where parts of the jet appear to be moving faster than light. Spoiler alert, they're not. It's just a trick of geometry and time delays. When something moves toward you at nearly light speed and emits flashes of radiation as it goes, those flashes arrive at Earth more quickly than they should. It looks like the blob is outrunning light. It's not. It's just playing tricks with your perception. Like every good magician, you fly through one of these radio lobes now. It's massive, bigger than the galaxy it came from. Particles here are no longer ordered. They're scattered, diffused, crashing into surrounding gas and heating it up. This whole region glows in radio waves. If you had ears tuned to that part of the spectrum, it would sound like static with meaning, white noise from a black hole's tantrum. There's another oddity here. You see cavities, giant empty-looking bubbles in hot gas. These are X-ray cavities, regions carved out by jets pushing back against intergalactic medium. It's like the jet punched a hole in space and left behind a void. Some scientists believe these cavities play a role in regulating star formation, essentially telling the galaxy when to chill out and when to get busy. Cosmic population control via plasma blaster. Subtle, and not all jets are created equal. You start noticing variations. Jets with knots, jets with curves, jets that break apart and reform like liquid light. Some of this comes from instabilities in the magnetic fields. Some from external interactions, gas clouds, companion galaxies, heck, even other black holes getting in the way. And sometimes, the cause is internal. The black hole's spin might change over time, its accretion disk might tilt, or maybe it just gets moody. We don't know. Historians still argue whether relativistic jets existed in the early universe, say, within the first billion years after the Big Bang. We found quasars from that era, sure, but were they already flinging light across the cosmos? The data's fuzzy. The redshifts are high. The debate is loud. and nobody's inviting the jet models to the dinner table without a big simulation to back them up. You finally begin to slow, not because your speed changes, but because the jet is fading. The particles are scattered now. The beam is done showing off. What was once a tight arrow of cosmic precision has loosened into a fog of memory, a lopsided ghost of the chaos it once carried. Still, as you drift here, in the wide quiet of post-jet space, you can't help but marvel. Light has made it, escaped, technically, from a place where nothing is supposed to return. Sure, the black hole didn't release it directly, but the processes right at the edge, at the brink of no return, managed to twist magnetism and matter into something bright, visible, and absurdly powerful. You glance forward, where stars begin to shine more normally again, unaware of the storm that passed nearby. Behind you, a fading streak of defiance, proof that even the darkest places in the universe can throw a tantrum loud enough to light the void. The beam you've been riding finally begins to fade from a brilliant collimated stream into something looser, broader, less a focused weapon, more a cosmic whisper. But don't mistake this for weakness. Even out here, thousands of light years from its source, the jet still pulses with astonishing energy. In fact, this is where it starts showing off to the wider universe, lighting up regions it was never meant to touch. And you drift gently now into the cosmic spectacle known as a quasar. You remember quasars from earlier, those quasi-stellar things that confused astronomers in the 1960s. What looked like ordinary stars in early optical observations turned out to be some of the brightest objects in the cosmos. Only when scientists cranked up their radio telescopes and tuned into X-ray and ultraviolet did the truth reveal itself. Quasars weren't stars at all. They were galaxies, young ones, powered by supermassive black holes with active accretion disks and jets that screamed through space like neon exclamation points. And here you are, gliding just outside the beam of one. It blazes across your field of view, a white-hot spotlight that drowns out the galaxy around it. The host galaxy is barely visible in comparison, washed out by the quasar's monstrous brilliance. It's like setting off a firework inside a foggy cathedral. Technically, the structure's still there, but good luck noticing anything but the boom. You drift sideways a bit, giving yourself a safer, more flattering angle. After all, you don't want to fly through the jet's main axis, not unless you're in the mood to be instantly vaporized by gamma rays. Quasars aren't just bright, they're weaponized. Here's something fun and slightly terrifying. Quasars can be visible from over 13 billion light-years away. That's how powerful their jets and accretion disks are. You're looking at ancient light, photons that started their journey before Earth even existed. And they're still this bright. Imagine being so loud the entire universe hears you scream across time. That's a quasar. The jet slices into the surrounding intergalactic medium, shocking and compressing it. A bow shock forms, an invisible tsunami of energy pushing gas into great arcs. You pass through one of these waves and feel the temperature rise, millions of degrees. X-rays hum around you. The magnetic fields are weaker here, but the energy isn't. It's just been spread out, like the echo of a scream in a cathedral, bouncing off every surface. And it's not just energy out here, it's matter. The jet carries particles, electrons, positrons, and the occasional heavier ion into the void. When these slam into intergalactic gas, they create radio lobes, great billowing clouds of glowing plasma. Some of these lobes stretch for millions of light years, far beyond the edges of their parent galaxies. You're looking at the long-term footprint of a jet that turned the void into a mural. Let's toss in a quirky historical nugget. The quasar 3C273, discovered in the 1960s, was the first confirmed quasar, and it's still one of the brightest. Its optical signature looks like a star, but its redshift told a different story. Turned out it was several billion light-years away. That much light travelling that far? Scientists had to radically revise their assumptions. Suddenly black holes weren't just endpoints of stars, they were engines, and their jets were the exhaust pipes. You turn back to the beam and notice something peculiar. It's jittering. Not wildly, but enough. These little shifts, called jet precession, can happen when the black hole's spin axis wobbles over time. That wobble can be caused by interactions with another black hole, a warped accretion disk, or just the cosmic equivalent of sleep deprivation. Now imagine this, a jet that precesses in a wide circle over thousands or millions of years, sweeping its energy across the surrounding space like a rotating lawn sprinkler from hell. That's one way to explain the odd shapes of some radio galaxies, ones where the lobes don't point in opposite directions but seem twisted or S-shaped. It's not a glitch, it's choreography. You fly alongside the edge of a radio lobe now, huge, diffuse and glowing with ancient synchrotron radiation. The particles here are tired. They've travelled far, lost energy, and now drift gently, fading into background static. But the memory of the jet remains, etched into the very fabric of space. And here's an open debate to spice up your journey. Do quasars evolve into normal galaxies, or are they just a phase that all large galaxies go through? Some astronomers argue that our own Milky Way once had an active quasar core and simply quieted down over billions of years. Others think only a subset of galaxies, those with a plentiful supply of infalling matter, ever reach quasar status. The data? Conflicting. The theories? Endless. The arguments? Delicious. As you float through the quasar's outer influence, you notice something else. Feedback. The jet isn't just a fire hose, it's also a regulator. By injecting energy into its surroundings, it prevents nearby gas from cooling and collapsing into new stars. This AGN feedback, that's active galactic nucleus, if you want to impress a date at a space-themed trivia night, plays a critical role in galactic evolution. Without it, galaxies might grow too fast, too bloated, too messy. Jets provide the universe's version of tough love. You pause, letting your momentum carry you into a quieter pocket of intergalactic space. The beam is behind you now, still visible but growing fainter. Around you, the stars are dim, the gas is thin, but the echoes remain. You've just flown through a process that takes millions of years, powered by an object that collapses space, time, and logic into a single gravitational scream. Still, it's not chaos. Not entirely. There's structure to it. The jet's formation, its direction, its light. All come from laws of physics that somehow still hold true even near the edge of forever. Gravity, magnetism, motion. That's all it took to shine light from the darkest place. You look back once more. The quasar is still shining, still beaming light across time. Somewhere, maybe a few billion years from now, some alien species will see it for the first time. To them, it'll be new, fresh, a mystery, and the jet, still travelling, still escaping. The darkest object in the universe made something bright enough to last forever. The light fades behind you, and you drift into a stretch of quieter space. The jet now a thread in the distance, more suggestion than substance. You're floating in the vast wake of something that once howled across the galaxy like a spotlight welded to a tornado. But not all black hole jets roar forever. Sometimes they sputter, they fizzle, they get interrupted. Tonight you witness one such jet dying. At first, it's subtle. The stream begins to flicker, a hiccup in the energy supply. You've seen what it takes to launch a jet, a spinning black hole, a ravenous accretion disk, twisted magnetic fields. But that's a delicate balancing act, and the universe doesn't care about keeping the lights on. Maybe the black hole's meal ticket finally ran out. Maybe the accretion disk thinned out. Maybe something disrupted the magnetic field scaffolding, and now the jet is crumbling like scaffolding in a windstorm. You glide back toward the base of this particular black hole, tracing the beam in reverse. It's a different beast than the quasar you just visited. Smaller, quieter, older. The accretion disk is still there, but it's dim, sparse. No fresh stars are being shredded into it. No major clouds are feeding it. This one is coasting on fumes. The jet itself flickers intermittently, on, off, on again, like a strobe light at the end of the universe. These intermittent jets have been observed before, sometimes in galaxies like Hercules A, where the jets appear disjointed or layered, as though they've turned on and off across cosmic time. It's not entirely clear what causes the switch. Some astrophysicists suspect black holes enter active phases depending on how much fuel they get, like a space engine cycling through full burn and idle. Others think mergers or disk instabilities may play a role. And here comes the weird part. While the jet's power source falters, echoes of its past activity remain. You hover near a ghostly radio lobe, a balloon of particles inflated long ago when the jet was at full throttle. But now the lobe is fading. No fresh particles replenish it. The outer edges have cooled, the radiation redshifted into oblivion. If this lobe were a city, the lights are still on, but nobody's lived there in 1,000,000 years. Even in death, these jets leave scars across the universe. You glide past one such remnant, a long, narrow cavity in X-ray gas, carved by the old jet when it blasted through this region. The black hole may be quiet now, but the galaxy still remembers the slap. Let's detour slightly and visit a stellar mass black hole, not the skyscraper-sized supermassives you've been hanging around, but something more compact. These guys, just a few times the mass of the Sun, can produce jets too, but they're smaller, more temperamental, and often powered by feeding on a companion star. You watch as one such stellar mass jet sputters in real time. The black hole's companion, a bloated red giant, is puffing off material into a shared accretion disk. But for reasons unclear, the transfer rate slows. Less matter reaches the inner disk. Magnetic fields weaken. The jet stutters like a dying flame. A final pulse of plasma shoots out, catching the last light of X-ray radiation, and then nothing. Historians still argue whether these interruptions in jets are caused primarily by magnetic reconnection failures or instabilities in the accretion disk itself. Some simulations suggest that magnetic field loops can tangle and break, collapsing the channel that maintains the jet. Others propose that matter in the inner disk simply cools too much and can't reach the temperatures needed to sustain the outflow. The fight continues, in simulations, in papers, and at awkward conference lunches. You turn your attention now to jet asymmetry. Some dying jets appear to fail on one side before the other. It's as if one magnetic pole sputters out first. These one-sided jets have been observed, baffling astronomers for decades. Are they truly one-sided, or are we just seeing one beam while the other's pointed away, and Doppler dimmed into invisibility? Oh, and here's your fringe theory of the night. Some researchers once speculated that jet interruptions could be caused by exotic matter, hypothetical particles that pass through accretion disks and dampen magnetic field activity like a cosmic suppressor. It's not widely accepted, but hey, astrophysics is nothing if not open to a bit of bold chaos. As you drift along the remnants of this particular jet, you feel the difference. There's no collimation anymore, no sharp edges. The particles are bleeding outward into surrounding space, losing focus, losing speed. The jet has become a ghost, and yet, not entirely dead. Some of these faded jets still emit in low-frequency radio, barely detectable. You'd need giant interferometers, like LOFAR or the SKA, to even tease the signal from the background hiss, but it's there, a whisper, proof that a monster once lived here and flung its light into the void. Back at the black hole, the accretion disk glows faintly, like embers in a fireplace after the logs are gone. The magnetic fields are still present, but weak. You can almost hear them crackling, reconnecting but unable to spark ignition. It's quiet, but not final. You wonder, could the jet come back? It's happened before. Some galaxies show evidence of restarted activity, where a dormant black hole gets a fresh meal, spins up its disk again, and reignites its jet after millions of years. These double-double radio galaxies have pairs of lobes, like cosmic matryoshka dolls. The older outer lobes remain as fading relics, while the newer jets carve fresh paths inside. So maybe this isn't death. Maybe it's just hibernation. You glide away from the sputtering remains, taking one last look at the structure once sharp and bright. The jet might be gone, but its mark on the cosmos is permanent. And if the black hole ever gets hungry again, well, you've seen what happens next. You pivot in space, drifting slowly, adjusting your view just enough to face the jet. Not from the side, not from above, but dead on. And now, you're in the line of fire. This, dear listener, is what it feels like to stare down the barrel of a blazar, a type of galaxy where one of those delightful relativistic jets you've come to know and love is pointed directly at you. You probably won't survive this, not because it's gory, this is still PG-13 bedtime science, but because the energy coming your way is laughably beyond comprehension. You're looking into a beam of plasma, radiation, and magnetic fury travelling at 99.999% the speed of light. You are, quite literally, in the crosshairs of one of the most focused sources of energy in the known universe. Congratulations. Blazars are what we call active galactic nuclei AGN with jets aimed at Earth. Not intentionally, of course, we're just lucky enough, or unlucky enough, to be sitting in the path. When this happens, everything we see from that galaxy is Doppler boosted, compacted, and exaggerated. The light gets brighter. The apparent motion of blobs in the jet appears faster than light. Hello again. Superluminal illusion. Even time seems to speed up. Fluctuations that happen over years in other galaxies can unfold in mere hours when pointed right at us. As you float in this direct line of sight, the jet becomes something different. Not a wide ribbon of energy, but a needle of light, sharp and narrow, pulsing with chaos. It's like staring into the high beams of a monster truck that's been chasing you across space since the Cambrian period. Let's talk flare-ups. Blazars don't just shine, they erupt. You're floating along as one of these events kicks off. A magnetic reconnection deep within the jet causes a sudden acceleration of particles. Bam! A gamma-ray flare. You see it before you feel it, because at this speed, the energy overtakes you almost instantly. Light hits, then particles, then shock waves. Your vision would go white if you had a face. The particles scream past you, and for a moment you're inside the very heart of the blazar emission. This isn't just synchrotron radiation now, it's inverse Compton scattering, where the electrons in the jet collide with photons, boosting them to gamma-ray energies. It's a violent process, and it's happening all around you, in every direction except behind. Blazars are divided into two main types: BL-lac objects, which have weaker emission lines, and flat-spectrum radioquasars, which have stronger ones. Both are dangerous. Both are showy. The difference lies in the structure of their central engines and how gassy their surroundings are. You're staring into one of the former: minimal fluff, maximum beam. A historical side note, blazars were initially thought to be oddball variable stars. It wasn't until the 1970s that scientists realized, oh, that's not a weird star, that's a black hole shouting at us. The name blazar itself is a mashup, BL-lac plus quasar. Scientists love puns, even when they're being vaporized. You drift a little farther back to get some perspective, and now the full structure unfolds. You're seeing more than just the jet. You're seeing the broad line region, a cloudy, fast-moving halo of gas near the black hole that emits light in complex patterns. Closer in is the dusty torus, glowing in infrared. Farther out, the narrow line region, where cooler gas slowly spirals under the influence of gravity and past radiation. All of these components interact with the jet. All of them shape what you see. The closer the beam is to your line of sight, the more amplified the madness becomes. And yet, despite all this energy, these objects are ridiculously far away. Some blazars are over 10 billion light-years distant. That means what you're seeing now happened when Earth's atmosphere was still figuring out how to not murder early microbial life. And despite that distance, they remain visible with even modest telescopes. That's how bright these things are. Let's pause and spice things up with a fringe theory. A few speculative astrophysicists have wondered whether blazars could be artificial, a cosmic lighthouse built by some ancient civilization to transmit energy or information across the universe. Maybe they're intergalactic communication beacons, maybe they're power stations, maybe... Okay, probably not. But the idea gets tossed around in SETI-adjacent circles from time to time, not because it's likely, but because the natural explanation is already so absurd, the leap isn't that far. Back to the beam. You're still riding it, or rather being pushed along by it. The energy density is so high that even the intergalactic medium is forced to rearrange. You're witnessing feedback in real time. The jet slams into a cold gas cloud far from its origin, heats it, ionizes it, and blasts it outward. This isn't just one galaxy lighting up the void, it's actively sculpting space on a galactic scale. Historians still debate whether these blazar jets influence the growth of their host galaxies, or if they're merely symptoms of that growth. Do black holes with jets help regulate the size of a galaxy's bulge? Or do the most massive galaxies simply have jets more often? It's a chicken and space egg problem. The answer is, as usual, it's complicated. You drift out of the line of fire now, orbiting just outside the beam's main axis. It's still bright here, but survivably so. The particles slow, the flare ends. The blazar settles down, for now. But you know it's just sleeping with one eye open. These things don't go quietly. They power up, burn bright, then collapse again into waiting silence. You glance once more at the host galaxy. It's barely visible, a ghost behind the beam. That's the curse of the blazar. So much light in one direction that it overshadows everything else. From Earth, we rarely see the galaxy that holds the monster, just the monster itself. As you drift into deeper space, the jet becomes a pinprick behind you, a warning flare, A reminder that even the darkest object in the universe can aim a beam so bright it outshines the stars it was meant to destroy. And if that beam happens to be aimed at you, duck. The blazer fades behind you now, no longer a threat but a blinking afterimage against the black canvas of space. You drift outward, far from the jet's deadly axis, into the wide, eerie regions shaped by events that ended long ago. What you're entering isn't a jet, not anymore. It's a memory, a phantom, a kind of cosmic bruise. These are the radio lobes, vast, ballooning structures of charged particles and low-frequency radiation that swell at the end of a black hole jet's lifetime. The jet itself may have long since sputtered out or quieted into dormancy, but out here, in the wake, the echoes remain. This is where the past lingers, and you're about to float through it. You coast through one lobe now, millions of light years across, barely structured, glowing faintly in radio wavelengths. These particles aren't screaming anymore, they're whispering. Long ago they were flung out at relativistic speeds, energized to near light speed fury. Now they drift, tired, bumping into particles in the intergalactic medium, gradually radiating their energy away. If you could see radio waves directly, this space would shimmer, not with light, but with texture, like soft ripples on water, turbulence frozen in time. It's haunting, really, the remnants of a cosmic tantrum stretched across a scale too big to grasp. You pass through regions where this jet's remnants pushed outward so violently, they created cavities in the hot plasma that surrounds galaxies. These are called X-ray cavities, and they show up in observations as strange holes in the gas. Not because something carved them in, but because the jet blew the gas out. Fun fact, some of these lobes contain more energy than 1 million supernovae combined. That's the kind of muscle these things flex, even in retirement. You glide past ghost cavities, regions once filled by a jet but now long empty. The lobe's energy has drained, the magnetic fields have decayed, and the radiation has redshifted so much that it barely registers. To a human eye, this would look like nothing. To a radio telescope, a whisper from 1 million years ago, a fading cosmic voicemail. And sometimes these lobes don't just fade, they echo. You watch as the edge of one lobe collides with a passing gas cloud. Shockwaves ripple outward, triggering new patterns. Some of that gas compresses. Under the right conditions, that compression leads to star formation. That's right, a black hole jet, long dead, still shaping galaxies, still seeding creation, light escaping the darkest places, and leaving behind stars. Historians still argue whether this kind of positive feedback, jets triggering starbirth, is common or rare. Most jets quench star formation by blowing gas out of galactic centers, but some, under precise conditions, seem to ignite it instead. Like a forest fire that accidentally fertilizes the soil. Your sensors pick up faint polarization patterns in the lobe, proof that the magnetic fields here still cling to some order, even after eons. These aren't chaotic remains, they're structured decay, fossils of force. And while you're marveling at this lobe, let's toss in something quirky. In the early 2000s, astronomers found radio phoenixes, structures that had faded entirely, then reignited when they were compressed by a passing shockwave. That's right, a long-dead lobe suddenly lighting back up like a cosmic ghost being poked by a stick. The black hole hadn't started feeding again, its leftovers had simply been disturbed. You drift closer to the outer boundary of the lobe, where the particles finally begin to slow enough to mingle with the intergalactic medium. This is where the line between jet and space begins to blur. You see small eddies, spirals of plasma curling like ocean foam. Here, the jet's energy disperses fully, becoming part of the background noise of the universe. And yet, even here, you find patterns. Filaments of magnetized gas stretch like veins through the emptiness. Particles still spin in wide arcs, held loosely by ancient fields. You feel it all, not as violence, but as residue. This is not the sound of war, it's the silence after, the quiet that reminds you something enormous once passed through. Then you spot something odd, off to the side, a smaller jet. But it's not coming from the black hole you just visited. It's coming from somewhere else, a companion galaxy maybe, or perhaps a dual black hole system where one jet outlasts the other. These systems are incredibly rare, but they exist. You're witnessing the fading remnants of two black holes, each with their own jets, each sculpting the space around them like rival graffiti artists tagging the same wall. One jet has gone quiet, the other still hums. Their radio lobes intersect, merge, twist into new patterns. And this collision, it might be temporary. The lobes may separate again, or they might entangle forever, leaving behind a warped asymmetric relic that will confuse future astronomers for eons. Space doesn't always clean up after itself. Now here's a historical tidbit. Cygnus A, one of the first powerful radio galaxies ever mapped in detail, has immense lobes like these. Scientists originally thought they were stars or other galaxies. It took high-resolution radio interferometry to realise they were the end zones of a jet, evidence that black hole outflows could stretch far beyond their host galaxies. You float through a structure like that now, not blazing, not lethal, but immense. You're inside the scar left behind by a beam of relativistic fury, and the longer you drift here, the more it feels like the universe itself is still echoing. This is how black holes speak long after they go silent. You pass one final edge of the lobe and glance back. The glow is faint, fainter than starlight, but it persists, a shimmer in the dark, a story told in radiation. The jet may be gone, the black hole may be quiet, but the message remains. You leave the vast silence of the ghost lobe behind, dipping back into more chaotic space, less serene, more bite-sized. Because now, you're shrinking your scale. You're moving from the grand cosmic performance of supermassive black hole jets to something far more intimate. Welcome to the unpredictable world of stellar mass black holes and their delightfully unhinged little jets. These black holes aren't millions or billions of times the mass of the Sun. They're more like 10, maybe 20. They're born from the collapse of massive stars, supernova leftovers that said no thanks to neutron star status and took the full plunge. But don't be fooled by their size. These black holes may be small, but they're jets, loud, unstable, and dramatic. You're drifting near one now, a classic X-ray binary system. That's a fancy way of saying a stellar mass black hole in a toxic relationship with a regular star. The black hole pulls matter from its companion, forming a compact accretion disk. The process is messy. Gas spirals inward, heats up, and glows in X-rays. But here's the fun part. Even in this tiny contained chaos, jets can form. And they do. Violently. Unlike the long sustained jets from quasars and radio galaxies, these jets are often episodic. Short, furious outbursts of plasma that shoot out from the poles when conditions align just right. You watch as the accretion disk brightens suddenly. Some instability inside has dumped a surge of material inward. Magnetic fields twist, reconnect, and boom. A microjet explodes outward, a compact beam of relativistic particles stretching light years into space, even though the black hole itself could fit inside Manhattan. Let's throw in a mainstream example. The famous system GROJ 1655-40, a stellar mass black hole in our own Milky Way, has been observed spitting out plasma at about 90% the speed of light. Incredibly fast, incredibly unstable. One moment it's a quiet X-ray source, the next it's hurling jets into space like an over-caffeinated fire hose. You float alongside such a jet now, watching its edges blur. It's shorter, yes, less focused than its supermassive cousins. But there's a raw, animalistic power to it. It doesn't stretch for millions of light years. It barely reaches a few, but the energy density, ridiculous. This thing was launched by something only a few kilometers across. It's like a house cat flinging a thunderbolt. These systems often exist in binary form, with the black hole slowly cannibalizing its stellar companion. You glance at the donor star, a bloated, unstable giant with a stream of matter pouring toward the accretion disk. It's like watching honey drain from a cracked jar in slow motion. Gravity doesn't rush, it pulls patiently. And here's your quirky tidbit. Some of these systems go through a process called state transitions, where the accretion disk flips between soft and hard states, depending on how much material is falling in and how it behaves. Jets usually emerge during the hard state and vanish during the soft. Why? That's still debated. It's like trying to figure out why your toaster only works when your kitchen light is off, but much, much faster. And with gamma rays, you watch this jet flicker, then dim. It's over. That outburst is done. Maybe it lasted a day, maybe an hour. In some systems, like V404 Cygni, the jet activity is even more rapid fire. Short bursts of plasma erupting every few minutes during a feeding frenzy. It's like cosmic popcorn. Pop, flare, fade. Pop, flare, fade. But not all jets in these systems are small. Some microquasars, yes, that's a real term, can launch jets hundreds of light years long. The name comes from their similarities to quasars, just on a mini scale. Same mechanisms, same drama, less real estate. Historians still argue whether microquasars should be considered scaled-down versions of supermassive jet systems, or if they're fundamentally different in how they handle magnetic fields and angular momentum. Some say, if it spits plasma and eats stars, it's a quasar. Others argue that scale changes everything. Welcome to Academic Hair-Splitting Astrophysics Edition. You drift past another stellar mass system now, this one in the middle of a small cluster of stars. The black hole's jet has carved a small cavity in the surrounding gas. Nothing on the galactic scale you've seen before, but noticeable, measurable. The feedback is real, even here. These jets heat their environments, stir nearby matter, and sometimes even clear away gas that would have formed new stars. Yes, even tiny black holes can shape their local neighborhood. It's like learning your neighbor's dog has secretly been designing the landscaping. And here's your open scholarly debate. Is the jet production in these systems driven more by the spin of the black hole or by the state of the accretion disk? If you had a perfectly still black hole with a raging disk, would you still get a jet? Or does the hole need to spin to create the magnetic flux required? The physics is murky, the simulation's contradictory. Welcome to jet theory, where the only thing we agree on is that no one agrees. You pass near a newly formed black hole now, fresh from a supernova, barely settled. It hasn't formed a disk yet. No jet, just gravity and darkness and potential. But you can feel it. Given the right companion, the right feed, the right spark, it'll join the party. And then something remarkable catches your eye. A system where the jet is misaligned. The black hole's spin axis doesn't match the orbit of the accretion disk, so the jet wobbles, precesses, creating a helical pattern through the interstellar medium. It looks like a corkscrew drawn in glowing ink across the stars. These patterns can persist for centuries, even millennia, marking the sky with long-forgotten geometry. Before you drift on, you pause beside a faded jet, one long gone cold. The black hole is still there. The companion star still orbits it. But the disk is quiet now. No flares, no outbursts. The jet's been off for decades, but the imprint remains. Light years of faint plasma cooling slowly in space, like the steam trail of a rocket long after the launch. And in that silence you remember, black holes aren't always loud, but when they are, even the little ones scream. You linger in the wake of the little jet, floating gently as the last particles bleed into surrounding space like exhaled breath in cold air. But now, you're pulling back again, zooming out from the compact chaos of stellar mass tantrums to a scale where entire galaxies bend under the influence of a jet. And tonight, you're about to see how those jets don't just light up the cosmos, they reshape it. You're drifting into the realm of the feedback loop, the process by which black hole jets don't merely exist, but actively influence the formation, structure, and future of their host galaxies. And yes, it's exactly as powerful as it sounds. One beam of plasma, born near an event horizon, can stop stars from forming halfway across a galaxy. No pressure. Let's begin with the basics. You float through a massive elliptical galaxy, bloated and ancient but oddly quiet. Not many new stars here. The gas is hot, too hot to collapse, and that's your first clue. This galaxy has a black hole that launched a jet millions of years ago, and the energy from that jet injected heat into the interstellar medium like a cosmic space heater on full blast. You see the results firsthand. Giant cavities carved in the hot X-ray gas, places where jets once inflated massive bubbles. Those bubbles now rise like smoke rings in a swimming pool, transporting energy far beyond the galactic core. It's not just pretty, it's regulatory. The jet may be gone, but its effects linger. Star formation here has slowed dramatically. Without cool, dense gas clouds, the galaxy can't build new stars efficiently. What remains is an aging population of red, dying suns, a stellar retirement home. Now you coast past a cool core cluster, a collection of galaxies huddled around a dense knot of hot gas. At the centre, a supermassive black hole with a history of repeated jet outbursts. Each outburst acts like a thermostat, preventing gas in the core from cooling too quickly and collapsing into an overstuffed galaxy. This is AGN feedback in action, the process by which black hole activity regulates the growth of galaxies. And yes, this idea was once deeply controversial. Historians still argue whether feedback was first seriously proposed in the context of radio galaxies in the 1970s, or whether its full implications only dawned during simulations in the 2000s. Either way, it's now clear. Without these jets, many galaxies would look very different. Some, in fact, might be too massive. Theoretical models once predicted far more giant galaxies than we observe. It was only when feedback was introduced, jets blowing away star-forming gas, heating surrounding halos, that simulations started to match reality. Jets, it turns out, are the universe's way of saying, "Slow down, buddy." But the story isn't so one-sided. You turn to a spiral galaxy now, less massive, but with a different kind of jet. Here, rather than shutting down star formation, the outflows seem to be stirring things up. You see gas clouds compressed by shock fronts, filaments of plasma wrapped around potential stellar nurseries. It's subtle, but in certain regions, stars are actually forming because of the jet. So yes, sometimes jets quench, sometimes they ignite. Welcome to the messy middle ground of astrophysics, the place where no theory applies to everything, and every exception demands its own name. Speaking of exceptions, let's look at jet precession. You hover near a galaxy where the jet's path has curved over time, either because the black hole itself is wobbling, or because another black hole is tugging on it gravitationally. The result? A strange S-shaped structure in the surrounding gas. It's beautiful. It's broken. It's confusing. Astronomers love these kinds of objects because they force models to get creative. You drift farther and begin to notice patterns. Galaxies with strong jets often have lower star formation rates. Galaxies with shorter, less active jets seem to have more ongoing starbirth. But the relationship isn't perfect. There's still an open debate over how much energy needs to be deposited, and where to either suppress or trigger stellar creation. Some researchers believe that the angle of the jet matters. If it fires perpendicular to the galaxy's disk, it escapes without much interference. But if it punches through the disk itself, chaos ensues. Shredded clouds, collapsed cores, stirred gas, like a blender with questionable timing. Let's pause for a quirky historical tidbit. In the 1990s, a few researchers proposed that some elliptical galaxies might have invisible jets, ones that had turned off long ago, but whose effects still shaped their environments. These fossil jets could only be detected by their lingering heat signatures or strange gas motions. Not everyone bought the idea at first, but today we see evidence of past activity in many quiet galaxies. And here's a fun fringe idea. Some scientists have proposed that galaxies might self-regulate their growth through a black hole jet feedback mechanism, acting like a thermostat. When gas piles up, star formation spikes, feeding the black hole. The black hole launches a jet which clears out the gas, cooling the galaxy down again. Rinse, repeat. A cosmic HVAC system, if you will. You drift near a simulation now, yes, a digital galaxy, built inside a supercomputer. Here, astrophysicists have modelled the feedback cycle. You watch and fast forward as gas collapses, stars ignite, the black hole feeds, a jet launches, gas is expelled, and everything resets. It's hypnotic. And it's based on real physics. Well, mostly. The equations are simplified, the assumptions tweaked, but the cycle is real. And it's not limited to galaxies. In galaxy clusters, jets can influence entire regions of space, heating intergalactic gas, driving turbulence, even altering how smaller galaxies evolve within the cluster. You hover at the edge of one such cluster now, watching faint X-ray loops arc across the sky, silent proof that jets from the central galaxy once blew bubbles the size of solar systems. All of this, all of it, traces back to something as tiny as an event horizon. You float above one now, staring down into the blackness. The jet is gone. The feedback echoes remain. A single point in space has shaped galaxies, ignited stars, and halted cosmic growth. That's the loop. That's the power. And as you start to slow, preparing to enter the calm between sections, you realize these aren't just streams of light. They're levers. The black hole reaches out, not to destroy, but to influence, to balance, to whisper across a galaxy and tell it when to shine and when to wait. The journey is far from over, but for now, let's breathe. Slow the pacing. Soften the cadence. You float again in silence, deep dark silence. Not the silence of nothing, but of everything at rest. The last gasps of old jets fall behind you. The fire, the pressure, the radiation, all fading now into a cool hum. You're surrounded by vast dim clouds, unshocked, unshaped, untouched. The kind of places where stars might still be born in peace. There's no urgency here, no beam to dodge, no X-rays to scorch your imaginary skin. Just soft waves of microwave background, drifting like distant lullabies from the early universe. You feel your momentum slow. You're still moving, of course. You always are, but gently now. No longer flung by plasma or driven by magnetic rage, just coasting. A cool blue glow cradles your view, diffuse, distant, eternal. A halo of forgotten photons. Maybe the edge of a radio lobe. Maybe just the light from a lonely galaxy whose black hole never got loud. You can't tell. And it doesn't matter. The silence deepens. You've seen light escape the darkest places. You've ridden jets, watched galaxies shift, seen feedback loops carved in plasma. And now, you rest. Let your thoughts soften like the edges of a dying star. Let your breath match the heartbeat of space. No more brightness, just the shimmer of memory, just the glow of what was. Just this. You begin to stir again, slowly rising from that lull in the void. Your senses sharpening, though gently, like the first ripples on a still lake. You've drifted through dying jets, faded lobes, and whispering galaxies. Now, it's time to come face to face with something more focused, more vivid, more photogenic. Welcome to M87, home of the most iconic black hole portrait ever taken. And yes, she has a jet. A very good one. You glide into the Virgo cluster and there it is, Messier 87, a supergiant elliptical galaxy lounging near the cluster's core. From a distance, it looks quiet, composed, but you know better. At the centre of this massive, bloated collection of stars lies a black hole so big, it makes your last few stellar mass friends look like marbles. This thing weighs in at 6.5 billion solar masses, and it's hungry. Now you approach her slowly. There's something regal about it. You pass through the outer halo of M87, through soft arcs of ancient stars, all pulled into lazy ellipses by gravity. The central bulge glows faintly, its starlight blurred by dust. And then you see it, the jet. Not imagined, not theoretical, visible. It stretches nearly 5,000 light-years, a sharp, elegant spike of radiation piercing through the galaxy's edge like a silver sword. The first thing you notice is its brightness. Brighter than it should be, brighter than anything else near it. Even in visible light, this thing glows. That's rare. Most black hole jets are best seen in radio or X-rays, but M87's is so intense, so concentrated, that you can actually see it with amateur telescopes from Earth. And this jet, it doesn't meander, it doesn't wobble, it fires straight, blazing out of the galaxy's core with the confidence of a flamethrower in a wind tunnel. You float alongside it, just a few dozen light years out, and watch the beam ripple. Inside, knots of plasma pulse and twist. These aren't smooth streams. They're chaotic, energetic clumps moving at relativistic speeds, blobs that seem to flicker in and out of existence. And here's the glorious part. We've seen this jet change in real time. Using telescopes across the electromagnetic spectrum, astronomers have tracked the movement of these bright knots. Over years, you can literally watch them shift. A living jet. A visible pulse of power launched from a point no wider than our solar system. Let's pause for the historical highlight. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, and it was this very black hole in M87. After years of global coordination, petabytes of data, and algorithmic wizardry, we saw it. A glowing ring of light, a dark center, a gravitational abyss framed in radiation. And that ring? It wasn't the black hole itself. It was light emitted by the inner edge of the accretion disk, warped into a circle by the intense gravity. You saw photons doing impossible things, bending, orbiting, stretching, and still escaping. That image wasn't just a photo. It was a victory for physics. But back to the jet. As you travel farther along it, you notice how tight the collimation is. The jet remains narrow for thousands of light years, even as it punches through surrounding gas. That's not easy. Something must be holding it together, likely a powerful magnetic spine twisted by the black hole's spin. This is the heart of the open debate. What exactly powers M87's jet? Most models point toward the Blandford-Znajek process, where magnetic field lines extract rotational energy from the black hole itself, but others argue for the Blandford-Payne mechanism, where the accretion disk plays the bigger role. Or perhaps it's both, or maybe it's something we don't understand at all. Historians still argue over when the jet in M87 was first observed. Some credit Heber Curtis in 1918, who noticed a curious straight ray coming from the galaxy. That was before anyone even knew what a black hole was. Imagine spotting a relativistic jet before relativity itself had finished unpacking its luggage. You slow now, hovering near a bright knot in the jet. Plasma swirls, radiation arcs. You feel the electrons spiraling along magnetic field lines, emitting synchrotron radiation in the radio band. This is where the jet starts to interact with surrounding space, where it begins to lose energy, slow down and disperse, but not before leaving its mark. You trace the jet's path out to where it begins to fade, where it starts to seed a faint radio lobe, a smaller one than you've seen before, but no less meaningful. This is what M87's black hole does. It carves the sky with light. It takes in matter, spins it, warps it, and throws it outward in a laser of plasma that travels across the stars, and for all this fury, the black hole itself stays silent. You return briefly to the core, not the ring, not the disk, but the shadow. There it is again, that soft, dark heart surrounded by flame. You hover at the photon sphere where light can orbit the black hole in perfect circles, defying logic. You catch a glimpse of your own trail of light bending back toward you. If you waited here long enough, you'd see yourself arrive. Time and space lose meaning in this place. Here's a quirky detail. In recent years, researchers analysing M87's jet found evidence that it might rotate as it travels, suggesting that the disk's spin is somehow transmitted along the jet itself. That's right, the black hole may be twisting space-time hard enough to impart angular momentum to the beam. As if flinging light wasn't enough, it wants to twirl it too. And now, you start to rise above the galaxy, looking down on M87 from above. The central bulge glows orange with old stars. The jet punches outward like a spotlight through a snowstorm, and somewhere, buried in that soft shadow of light and gravity, lies the quiet beast who launched it all. This is the moment when you realise, this isn't just light escaping the dark, it's order emerging from chaos. A structured stream launched from a place where even time forgets its name. A message sent through magnetism and motion. M87's jet has been burning for millions of years. It will likely burn for millions more. And it's not just seen, it's felt, across space, across minds, across the boundary between theory and proof. You drift onward, knowing you've seen the black hole that stared back. You're drifting now through the afterglow of M87, your path curling away from its luminous jet and back into deeper space. But the further you pull away, the more a question tugs at you, quietly, relentlessly. What really powers these jets? You've seen accretion disks spin, magnetic fields twist, particles accelerate, and light erupt from gravity's final trap. But what's the core ingredient? What flips the switch? What gives a black hole the ability, not just the opportunity, to fire a beam of plasma across intergalactic space? And so you dive back toward the source, not into the jet this time, or the disk, or the fading lobe, but into the black hole itself, or rather, just above it. Because now you're here to confront the spin conundrum. At the heart of this debate lies a deceptively simple question. Does a black hole's spin determine its jet power? Seems intuitive, right? Spin equals power. The faster the black hole rotates, the more it twists space-time, and the more energy it should be able to extract and throw into a jet. But reality, as always, has opinions. Let's build the picture. You're hovering at the edge of the ergosphere, the region around a rotating black hole where space-time itself is being dragged along. You feel it, not as motion exactly, but as a pressure, a swirl, like being caught in the eddy of a river with no water. This frame-dragging effect is unique to Kerr black holes, the spinning ones, and it's this drag that might let us extract energy directly from the black hole's rotation. That's the Blandford-Znajek process, and yes, we're bringing it back. The idea is that magnetic field lines anchored in the ergosphere can siphon off the black hole's rotational energy, channeling it into the poles and firing it away as a relativistic jet. It's elegant, predictive, mathematically sound, and yet, historians still argue whether this is the dominant mechanism in real astrophysical systems. Some simulations support it, others find too many dependencies. The jet's power doesn't always scale cleanly with the estimated spin rate. Some slow-spinning black holes still launch powerful jets. Some fast spinners seem surprisingly quiet. So, what gives? That brings us to Team Accretion disk. In this camp, the Blandford-Payne process takes center stage. Here, the disk itself plays the lead role. Magnetic field lines extending from the surface of the disk, not the black hole, act like tensioned wires. As the disk spins, those lines twist and matter follows the spiral upward, launching jets, even without strong black hole spin. You hover above one such disk now. It's thick, bright, spinning fast. The black hole beneath you might be barely rotating, but the disk, it's throwing tantrums. Magnetic turbulence ripples through the gas. You see particles shoot upward from the disk's inner edge, not the event horizon, launched by magnetohydrodynamic fury. Could it be that jets come more from where the energy is, rather than what the black hole is doing? And yet the debate gets messier. Some researchers argue it's not either or, it's both. That black hole spin provides the raw power, and the disk decides how much of it gets turned into a jet. That both processes can happen at once, sometimes cooperating, sometimes competing. You glide past another system, this one newly fed by a collision. A gas cloud has just been devoured, reigniting the accretion disk and spinning it wildly. Within weeks, a jet flares into life. But here's the twist. The black hole's spin hasn't changed much. It's the disk that came alive. So what powered this? This is where the spin conundrum gets real. Because spin alone doesn't seem to explain everything, and disk behavior, while crucial, doesn't either. Some researchers suggest a third variable, magnetic flux accumulation. The idea is that jets only launch when enough magnetic pressure builds up at the black hole's poles. It's not just spin, it's not just flow, it's whether the system reaches a magnetically arrested disk, or MAD state. You pass through such a system now. The magnetic field here is so strong it chokes the inner accretion flow. Gas piles up, struggling to fall inward. Magnetic pressure dominates. When the dam finally breaks, it sends an eruption upward, and a jet is born. But only after a long, chaotic prelude. Still, not every system gets MAD. Some black holes feed gently, magnetically poor, too calm to build jets. You float near one now, quiet, bloated, but jetless. It spins fast. It has an accretion disk, and yet, nothing. Why? That's the question. Why do some black holes with all the right ingredients not form jets? And why do others, smaller, less massive, more chaotic, produce powerful beams? You check back on observational evidence. The Event Horizon Telescope's image of M87's shadow suggested its black hole is indeed spinning rapidly, perhaps even near the theoretical maximum. That supports the spin model. But then there's Essa Grey Star, the black hole at the centre of our own galaxy. It also seems to spin, and yet no jet. Historians still point to earlier X-ray binary studies for hints. In those smaller systems, jet power often correlates loosely with estimated spin, but not always. Some low-spin black holes still flare, some high-spin systems stay quiet. The data, like the jets, is inconsistent. You pause now, floating between systems, one spinning like mad but silent, one rotating slowly but flaring with plasma, and you realise the spin conundrum may not be a question of what powers the jet, but rather what conditions let that power escape. It might be alignment. Is the black hole's spin axis lined up with the disk? Misalignment could create turbulence, cancelling the jet, or it could spark precession, bending the jet into corkscrews. It might be magnetic connectivity. Are the field lines well anchored? Are they strong enough to hold together a beam? Or do they unravel before anything launches? Or maybe it's the scale of observation. Jets may vary so much across size and time that no one answer fits all. Supermassive black holes behave differently from stellar ones. Different fuels, different surroundings, different moods. Yes, moods. These things are dramatic. Here's your fringe theory for the night. Some theorists have wondered if quantum effects near the event horizon could influence jet formation. Virtual particles becoming real, spin states affecting magnetic reconnection, even speculative ties to the black hole's internal entropy. It's all deeply speculative, but it shows how far we are from certainty. You return to the edge of a spinning black hole now, one that's launching a moderate jet. Not too weak, not too strong, everything is aligned just right. The disk is hot, the field is strong, the black hole spins, and together they beam matter across space, not because one mechanism dominates, but because for this moment everything works together. You drift higher. The jet stretches away, narrow and bright. The disk hums, the black hole spins, and somewhere behind it all the conundrum spins too, unresolved, untamed, beautiful. You're coasting again, high above the plane of a galaxy bruised and battered by ancient fury. It doesn't look like much from up here, just a spread of stars, some glowing arms, a modest central bulge. But as you drop down toward it, the signs of trauma start to show. A huge cavity in the X-ray gas, dust lanes ripped apart, unusual stellar arcs. No, this isn't natural galactic aging. You're looking at a system that's been jet-lagged. Not in the airplane travel, forgot what day it is way, but in the astrophysical sense. This galaxy was hit long ago by a black hole jet, and the effects are still unfolding. You hover near the central region where the supermassive black hole now sleeps. The accretion disk has cooled, the magnetic fields have collapsed, the jet, long gone, and yet the galaxy still reels from what happened. You see asymmetries in star formation, cold gas disrupted, pockets of ionized material pushed into unexpected shapes. This is feedback that hasn't healed. You drift into one of these shock fronts, a gently curved arc of hydrogen gas still faintly glowing from a collision with a relativistic outflow that ended millions of years ago. The front moves slowly now, like the ripples of a long-ago cannon blast across a pond that forgot it was once violent. It's a good time to talk about galactic archaeology, the study of these cosmic bruises. Scientists now use multi-wavelength observations, radio, X-ray, infrared, to piece together the crime scenes of past jet events, not just in active galaxies but in normal-looking ones like this. Historians still argue which galaxy was the first to clearly show signs of ancient jet damage without an active core. Some cite Perseus A, with its ghost cavities. Others point to NGC 1266, where a strange molecular outflow suggests past AGN violence. Either way, the evidence builds. Galaxies can suffer from post-jet stress. You dip toward a filament of ionized gas, threading through the galactic halo like the trail of a smoke ring that never quite faded. It winds through the remains of star-forming regions that once thrived, now depleted. The cause? A jet that passed through here ages ago, heating the gas past the threshold for collapse. Stars stopped forming, but the structures remained. Beautiful, barren, like a coral reef after the water's gone warm. Here's a quirky observation. In some galaxies, young stars have been found aligned along the paths of ancient jets. One theory is that the jet compressed gas into star-forming clouds as it pushed through the galaxy. Another says it simply cleared the way for existing gas to fall inward. Either way, the result is a kind of jet trail of stars, stretching across the disk like breadcrumbs. And not all the trauma is visual. You hover over a region of the galaxy where the gas spins wrong, counter to the stars. This kinematic misalignment is another sign of past disruption. Something injected angular momentum into this gas, spun it the other way. Maybe a merger, maybe the jet itself. You begin to notice a pattern. Regions near the jet's former axis show lower star density, higher gas temperatures, but farther out, off-axis, the galaxy is still forming stars. It's like the jet punched a tunnel of silence through the core while life continued around it. This kind of selective impact is part of what makes AGN feedback such a headache to model. It's not even, it's not clean, it's targeted, chaotic, lopsided. Some researchers now argue that many galaxies show subtle evidence of old jet activity, even if they look quiet. Not from obvious features like lobes or cavities, but from their internal structure. Slight metallicity gradients, irregular halo temperatures, disrupted dark matter cores. The ghosts of jets live everywhere. You glance toward the edge of the galaxy now, where a wide arc of diffuse stars curves in an unexpected direction. Could this be a relic lobe, once lit up in radio, now dimmed beyond detection? Possibly. In the past few decades, ultra-deep surveys have revealed more of these relics, old inactive jets that only shine in the lowest frequency radio light, too faint for most instruments until recently. These are the fossils, the scars, the monuments, and some of them still dangerous. In a neighbouring galaxy, you observe an old lobe interacting with a cold gas cloud. The particles, though slow, still carry energy. When the jet matter slams into the cloud, it compresses the gas, waking it up. Star formation begins. Slowly, inefficiently, but undeniably. It's like a bear rolling over in hibernation and accidentally planting flowers. Here's your fringe idea of the night. Some theorists speculate that jet-altered gas clouds could drift into nearby galaxies, seeding them with enriched material or disturbing their own star-forming regions. The idea of intergalactic jet pollution isn't mainstream, but it raises a thrilling thought that a jet from one galaxy could change the fate of another. Cosmic splash damage. You drift through one such intergalactic bridge, a faint magnetized streamer of plasma still connecting two galaxies. It looks like a tendril of fog, but inside, you detect faint synchrotron radiation. A jet passed through here. And though the source galaxy is now quiet, this streamer still glows. Not visibly, not brightly, but persistently. Time passes strangely in this space. The effects of jets unfold over tens of millions of years, while the jets themselves might only burn for a few. It's like tossing a match into a dry forest and watching the ecosystem adjust over millennia. And now, as you pull back once more, you look at the galaxy in its full, quiet form. From a distance, you'd never know what happened here. It looks healthy, ordinary. But up close, you've seen the scars, the missing stars, the jumbled gas, the still glowing filaments that trace a beam of light from a hole in space. This galaxy is jet-lagged, not destroyed, not dead, just altered, and it will carry that imprint forever. You drift now through a quieter stretch of the cosmos, dim galaxies in the distance, the afterglow of jet-shaped scars fading behind you. But something strange begins to stir in your periphery. Not a beam, not a lobe, not a firestorm of plasma. No, this is subtler, fainter, a shape in the dark that never quite formed. You've come to the realm of ghost jets and false starts, the almosts of the black hole world. Not every black hole jet roars to life. Some whisper, some try, some fail. You approach the centre of a low-luminosity galaxy, where the signs are all there. A decent-sized supermassive black hole, a halo of hot gas, and even a faint accretion disk. You'd expect a jet here, but there isn't one. Instead, you find a relic filament, a narrow magnetized structure that glows only in low-frequency radio. A line of particles suspended in space like a bridge to nowhere. Once, maybe it was a jet, or the start of one, but something cut it short. You hover there, puzzled. Why would a black hole begin to launch a jet, then stop, or never fully commit? One theory suggests this was a frustrated jet, a jet born in a dense environment where surrounding gas was so thick it choked the outflow before it could escape. You can almost see it, particles streaming upward, only to be smothered, slowed, deflected. The result isn't a beam, but a bubble, distorted and dim, full of potential but no propulsion. Frustrated jets show up more often than you'd think, especially in galaxies rich with cold gas or in the early stages of a merger. Sometimes they form weirdly shaped lobes, asymmetric and malformed, giving away the drama of their aborted birth. You pass through one now. It's an oddly lopsided arc, glowing faintly in radio, but with no visible jet connecting it to the core. To an optical telescope, this would look like background fuzz. But here in your floaty little consciousness form, you can see the ghost in its full shape. It wanted to be a jet, but the galaxy wouldn't let it. Let's rewind for a moment to something even fainter, the phenomenon of jet mode switching. Some black holes don't just shut off their jets, they shift into different states, alternating between powerful outflows and weaker, more chaotic ones. You float near a galaxy where this has happened. The current outflow is barely detectable, but if you dig deep, through archived emissions, through old X-ray signatures, you find evidence that, once upon a time, this galaxy blasted jets thousands of light years long. So what happened? One possibility, the fuel changed. The accretion disk thinned out or became chaotic. The magnetic fields realigned or fell apart. Another, the black hole's spin axis may have shifted, reorienting the entire launch structure. When the components don't align, jets misfire or don't form at all. Historians still argue whether jet failure is primarily an issue of environment or engine. Some believe jets are stifled by dense gas or galactic structure. Others argue that it's internal. The black hole simply never built up enough magnetic flux, or never reached a spin state strong enough to trigger a beam. You drift into a nearby dwarf galaxy now. No jet here, just a quiet little black hole humming in the center. And yet, something happened. You spot a disrupted gas filament near the core, a puffed-out bubble of shock-heated hydrogen. A mini feedback bubble. Some scientists think small black holes in these galaxies produce jetlets. Low power, temporary outflows that don't leave lasting lobes, but still inject energy into their surroundings. They're not dramatic, but they matter. And here's your quirky tidbit of the night. In 2010, a team observed a double-lobed radio structure in a galaxy that had no visible jet, no bright core, and no accretion disk to speak of. It's since been labelled a fossil AGN, and no one's quite sure how to classify it. Some suggest a jet that flared briefly, then died. Others think it's the remnant of an older black hole, now kicked or moved, leaving its lobes behind like footprints from a ghost. Then there's the mystery of X-shaped radio galaxies. You pass through one now, two sets of lobes extend from the core, crossing each other like a celestial letter X. One set is active, the current jet. The other, fading, angled differently. This suggests a jet realignment event, possibly caused by a black hole merger where the spin axis flipped and a new jet direction took over. The old jet became a ghost. The new one burns bright. You float near the intersection, feeling the strange geometry of the space. It's like standing in a city with one abandoned highway and one under construction, both aimed toward different futures. And here's a fringe theory to chew on. Some astrophysicists have proposed that failed jets, especially those that eject particles without full collimation, could help seed intergalactic magnetic fields. That's right. Even the unsuccessful ones might be contributing to the invisible scaffolding of the universe, twisting fields into place that later shape galaxy formation. Failure, it turns out, might still be useful. You pause above a jet that launched unevenly, its northern beam well formed, its southern twin nowhere to be found. Observers call these one-sided jets, but you now know better. The other side may have been weaker, or aimed away, or smothered by gas. The asymmetry isn't failure, it's interference. And sometimes, interference is all it takes to silence light. You coast slowly now through the remains of a restarted jet, where a black hole turned off, then back on. The old lobes hang high above, barely glowing. The new jets haven't yet reached that far. The galaxy is layered, time-stamped in plasma. These double-double radio galaxies reveal the stop-start nature of black hole activity. Not a single explosion, but a cycle, a strobe, a stutter. It's humbling. Even in failure, these jets leave marks. Even when the launch fails, the sky remembers. You glide through one last region. A strange one. A galaxy that should have a jet. All the signs are there. Accretion disk, strong magnetic fields, spin, but nothing. Just silence. Maybe it's timing. Maybe it's waiting. Maybe at this very moment the first threads of plasma are twisting into place. Or maybe not. Maybe it's the ghost of a jet that never was. You pivot now, turning away from ghosts and faded echoes, towards something bright, sharp, and alarmingly alive. It doesn't look like a galaxy. It doesn't even look like space. You're heading into a room, in a sense, a digital room, lit not by stars but by equations, monitors, code, fans humming in sync like some monastic chant. This is where black hole jets are built, not in the heavens but on Earth, in simulations and supercomputers where light-speed plasma, warped space-time and tangled magnetic fields are conjured inside the circuitry of modern science. Welcome to the lab. You glide over racks of hardware so dense they give off heat like newborn stars. Petabytes of memory, GPU clusters buzzing, liquid cooling winding through pipes like synthetic blood. No black holes here, but their mathematical ghosts live in every processor. And in the center of it all, a simulation running in real time. Not just pretty pictures. No, you're looking at a GRMHD model. That's general relativistic magnetohydrodynamics, for those playing along. It's the only way we've found to simulate jets properly, combining fluid dynamics, magnetic fields, and Einstein's warped space-time into one hellish soup of math. Inside this virtual black hole, particles swirl around a spinning singularity. The disk thickens, the magnetic fields tangle, and then it happens. The jet forms. You zoom in, watching plasma coil along magnetic field lines. It's like tracing lightning in slow motion. The jet sharpens, tightens, launches. The computer doesn't know how beautiful this is. It only knows tensors, fluxes, boundary conditions. Let's pause for a historical snapshot. In the early 2000s, simulations of jets were crude, 2D, non-relativistic, full of approximations. It wasn't until high-performance computing, and brave grad students, unlocked fully 3D GRMHD that the field exploded. Suddenly we could see jets form, watch disks warp, track magnetic reconnection in real time. The black box was no longer black. You coast past a screen displaying one such simulation's output. It's color-coded, false-colored, saturated, but the story is clear. A black hole spins at near maximum. A thick disk feeds it. Magnetic field lines, anchored to the event horizon, twist upward. Energy is extracted. A beam erupts. This model is running the Blanford-Znajek process to near perfection. And guess what? It works. The simulated jet looks exactly like what we observe in galaxies like M87 or 3C273. The opening angle matches. The collimation length fits. Even the plasma knots behave. Mostly. But not all simulations agree. Some show disk-powered jets taking over. Others struggle with turbulence, the real killer. Magnetic fields don't stay neat in real life. They twist, break, reconnect, flicker. Trying to simulate that chaos requires a careful balance between numerical stability and physical realism. Too smooth, and it's fake. Too messy, and the whole thing crashes. You hover now near a wall of research papers, each one an argument. Some claim that magnetically arrested disks, MADS, are necessary for jet formation. Others say standard and normal evolution, SANE disks, are enough. Acronyms abound, nobody agrees. Historians still argue over the first convincing jet simulation. Some credit early accretion disk models by Hawley and Balbus. Others point to McKinney's 3D-GR MHD runs in the 2000s. But one thing is clear. The minute computers could model jets in full relativistic detail, we entered a new era. You pass into another digital chamber, this one modeling a binary black hole merger. Now the simulation goes wild. The gravitational waves ripple, the disks collide, jets precess and flare like strobe lights. For a brief moment, two beams pulse outward, then one dies. The dominant black hole wins. The new spin axis locks in, the jet realigns. And here's your quirky fact for the night. Some simulations suggest that in these mergers, orphan jets might form temporarily. Jets that launch from disks without a black hole for a few seconds before falling apart. Jet imposters, one-hit wonders. You drift past another workstation where a simulation of a failed jet is being studied. The magnetic flux builds, but never reaches threshold. The field lines collapse. The disk winds down. The jet never ignites. The researchers aren't disappointed. This too is data. Here's the magic of simulation. You can test the cosmos like a sandbox. Want to see what happens if the black hole spins retrograde? Done. Want to feed the disk ion instead of hydrogen? Sure. Want to scale everything up by a factor of 10 just because? You bet. And yet, you can't model everything. You float past a board of variables left blank. Cosmic rays, radiation pressure, quantum effects, turbulent viscosity. These are the edges of the map. Unknowns we still fumble through, adding when we can, guessing when we must. Some simulations include synchrotron radiation, tracking where photons emerge from spiraling electrons. Others track polarization, predicting how light from a jet should twist as it travels through space. These models are matched to real observations of M87, of blazars, of gamma-ray bursts. The fit is never perfect, but sometimes it's terrifyingly close. Let's slide into fringe territory. You find a simulation labeled jet-dark matter interaction. It's experimental, controversial, barely cited. It asks, what if black hole jets stir dark matter? Could the outflows inject enough energy to affect halo profiles? Could jets shape the invisible universe too? Probably not. Maybe. Who knows? Simulations let us play in the realm of the possible. They don't prove reality, but they sharpen the questions. They show us what can happen under the right conditions. You glide through one last simulation, a black hole at the centre of a primordial galaxy, just 500 million years after the Big Bang. The disk forms, the field builds, and then, astonishingly, a jet erupts. Even this early, even this far back, light escapes the dark. The code doesn't care, but you do. You pull back from the simulation now, watching the digital jet burn brightly against the grid of space-time and equations. Somewhere in the real universe, a similar jet may be firing right now. Maybe from a black hole we'll never see. Maybe from one we already have. In these simulations, jets live and die in minutes. In reality, they burn for millions of years. But the physics is the same. Light, gravity, spin, magnetism, and just enough chaos to make it beautiful. You drift now from virtual models and glowing grids out once more into the real cosmos. But something's changed. You've seen jets big and small, graceful and catastrophic, successful and interrupted. You've learned the physics, the debates, the scars, and yet one last mystery still looms. The question is so simple it sounds almost naive. Do all black holes jet? You float through a quiet galaxy now, a spiral not unlike our own Milky Way. It's calm, no cavities, no lobes, no X-ray bursts or radio emissions slicing across the sky. Its central black hole sits tucked into a bright nuclear bulge surrounded by gas, stars and dark matter. But there's no jet. You approach the center expecting something. Anything. Maybe a flicker, a pulse, a whisper of plasma. But there's just quiet accretion. Material spiraling inward slowly like syrup down a drain. The magnetic fields are weak. The disk is steady. The spin of the black hole, still uncertain. You feel the question sharpening. Why do some black holes launch relativistic beams that stretch for millions of light years, while others, just as massive, just as well fed, stay dark? This is the jet dichotomy, and it's one of the great unsolved riddles of astrophysics. Let's lay out the players. On one side, we have radio-loud AGN, black holes that scream across the cosmos with powerful jets, blasting synchrotron radiation in radio, X-ray, even gamma. On the other, radio-quiet AGN, still active, still feeding, still glowing in optical and UV, but no jet, not even a stubby one. What gives? Historians still argue when the term radio loud was formalized. Some trace it back to the earliest catalogues of quasars, where a clear divide was seen. A small subset emitted strongly in radio, while most did not. That ratio holds today. Only about 10% of AGN are truly radio loud, which means jets are rare, selective, almost picky. You float near one of these quiet cores. The accretion disk is radiating. There's UV light, there's soft X-ray, but the plasma near the poles, listless, no twist, no launch. The black hole may be spinning, but if it is, the magnetic fields aren't cooperating. So maybe that's the answer. Maybe magnetic flux is the limiting factor. You remember those simulations, the ones that required a magnetically arrested disk to produce jets? Perhaps these quiet black holes just never gather enough magnetic field strength to cross the ignition threshold. But then again, some galaxies with strong fields still don't launch jets. So maybe it's more about black hole spin. A slow rotator can't provide the torque needed to twist field lines into a beam. That would fit with the Blanford-Znayak camp. But we've seen fast rotators without jets too, so not a perfect fit. And here's where things get messier. You drift into a merging galaxy pair, where two supermassive black holes spiral toward union. One has a strong jet, the other is quiet. The galaxies are similar, the disks are similar, even the surrounding gas is shared. So why the difference? One theory: black hole alignment. If the spin axis and disk rotation don't match, magnetic structures might never stabilize. Jets may form, wobble, then collapse before they fully ignite. Alignment could be a hidden switch, one we can't detect directly, but one that decides who gets to shine. Another theory involves host galaxy type. Elliptical galaxies tend to produce more radio-loud AGN than spirals. Why? Possibly because they harbour black holes that have experienced more chaotic growth, more mergers, more retrograde accretion, more opportunity for jet-favourable conditions. Spirals, by contrast, are steadier, cooler, and maybe just too polite. You float upward now, leaving behind individual galaxies to scan a field full of AGN. Some shine with jets, others don't. Some are Seyfert galaxies, compact and active, but barely radio-emitting. Others are liners, low-ionization nuclear emission line regions, faintly glowing cores with sluggish feeding and no beam to show for it. But then you find a surprise. A TDE, a tidal disruption event. A star has just wandered too close to a previously quiet black hole and been ripped apart. Gas floods the inner disk, magnetic fields ignite, and, suddenly, a transient jet erupts. Just like that, a radio-quiet black hole starts shouting. This, dear traveller, is a hint. Maybe all black holes can jet under the right circumstances. Maybe the silent ones are just waiting, sleeping, undisturbed. You hover above another galaxy, one that's been quiet for billions of years. But simulations suggest it may have fired jets in the past. Its stars show metallicity patterns consistent with old feedback. Its gas halo carries the faintest imprint of magnetized outflow. The jet is gone, but the memory remains. It makes you wonder, what if all galaxies cycle through jet phases? Like volcanoes perhaps, dormant most of the time. But when the conditions stack just right, fuel, pressure, heat, the eruption comes. Some last longer, some burn brighter, some barely get started. But the capacity may be universal. Here's your fringe theory. One proposal suggests that the dark energy field, yes, the one driving cosmic expansion, might couple, however weakly, with black hole spin or accretion. The idea that some hidden cosmological variable subtly regulates which black holes can jet. Wild? Absolutely. Proven? Not even close. But it shows just how desperate we are to understand the split. You float one last time through a jetless galaxy. No scar tissue, no shock fronts, just peace. And yet, you can feel it. Beneath the surface, in the way the gas orbits, in the faint flicker of the inner disk, there's potential, waiting. Maybe it will never ignite. Maybe it will flare tomorrow. Not all black holes jet, but all of them could. And that's the final unsettling truth. The silence of space is not a lack of violence. It's a pause between pulses. You rise now, slowly, steadily, drifting away from the patchwork of galaxies, lobes, beams, and ghosts that make up the cosmic jetscape. It's been a long journey through chaos, but now you're pulling back, out past the clustered clusters, past the filamented voids, past the scaffolding of the universe itself. Time slows again. The noise fades, and then you see it. Not one jet, not one black hole, but all of them. A map of the universe as it truly is, shot through with light escaping the unthinkable. You're floating outside time now, peering down across the epochs. The early universe glows dimly behind you, laced with the soft hiss of reionization and baby galaxies lighting up their first stars. But scattered among them, like arrows fired from darkness, are the first jets. Primitive, furious, raw. You watch one blaze through a forming galaxy, carving out cavities before its host even settles into shape. It's not elegant, it's not stable, but it works. The black hole, barely a few 100 million years old, launches a column of radiation that sculpts its environment before the first spiral arm ever curls. You drift forward. Billions of years pass. Galaxies grow, merge, die. Jets rise and fall. Some slice neatly through space, others corkscrew into ribbons. Some flicker on and off like faulty neon. Others burn straight for eons. You begin to notice patterns, cosmic graffiti painted by plasma and gravity. Here's a jet inflating a massive lobe in a galaxy cluster, slowing star formation across hundreds of thousands of light years. There's another one kindling stars at the edge of a filament, triggering beauty where it should have brought destruction. One black hole flares once and sleeps forever. Another lights up again and again, carving scars across space-time. The details blur now, but the big picture sharpens. Black hole jets aren't accidents. They're phenomena. They connect the tiniest regions of extreme physics, the event horizon, to the largest visible structures in the cosmos. They are the string between micro and macro, the scream from the silent. You pull even farther back now, until galaxies themselves shrink to points. The filaments of the cosmic web pulse faintly with the memory of ancient jets. Some lobes still glow, others have long since cooled, but their shapes remain. They've shaped everything, even the cold gas flows that feed galaxies, even the merger rates of clusters, even the metallicity gradients of deep cosmic time. Black hole jets don't just escape the dark, they order the dark. And yet, for all this reach, all this violence, all this impossible scale, it always begins the same way, with a single particle swirling into a disk, a single atom crossing the innermost stable orbit, a single magnetic loop catching and twisting, a spark. You return now to one such place. A black hole, not particularly big, not particularly loud, sits alone in a quiet dwarf galaxy. Its disk glows faintly in ultraviolet. No jet yet, just the conditions, just the whisper of potential. You've seen enough to know it might fire tomorrow, or 1,000,000 years from now, or never. But the rules are there, the math is waiting, so is the light. And maybe that's the strangest, most beautiful part of all this. That something as purely destructive as a black hole can produce light, not by kindness, not by miracle, but by the sheer mechanical consequences of physics. Gravity spins a disk, friction heats it, magnetism channels it, the universe finds a way. You've witnessed the full arc now, from the launch to the lobe to the collapse. You've seen jets fail, flare, flicker, feed. You've watched stars born in their wake and galaxies silenced by their fury. And still, it's not over. Jets will continue to fire long after Earth is dust, long after the Milky Way merges with Andromeda, long after the last red dwarf flickers out. They are among the longest-lived, most influential structures the universe knows, all from objects that do not let light escape, except this light, this carefully stolen, barely permitted, violently channeled light, this light that broke the rules, this light that escaped the darkest place. So next time you look at a tiny speck in the sky and hear someone say, "That's a galaxy," know this. It might also be a beam, a scar, a message sent by gravity, magnetism and entropy across billions of years, just to reach you. And now you've heard it, you've followed it, you've understood it. That's more than most will ever do, and if this light ever flickers your way, don't run, look up and whisper back. You float now in silence again, not the silence of absence but of completion. The journey has wound through chaos and calm, light and shadow, structure and decay, and now there is stillness. No more jets, no more flares, just you and the dark and the glowing thought of what you've seen. You're far from the center now, far from any black hole, any beam, any plasma storm. The space around you is soft, diffuse, not empty, but unbothered. Particles drift here without purpose. Magnetic fields curl lazily, like smoke in no hurry. Time stretches. There is nothing to do, nowhere to go, just quiet. You look back, if looking were still something you did, and see the faint traces of the things you've travelled through. A bright knot where a jet was born, a filament where it twisted, a lobe where it ended. Each one a memory now, drifting just like you. There's peace in that. You followed light from the edge of destruction, across the vacuum, into form, into silence. You've watched it make stars and carve space, beaming out from a place where nothing should escape, and yet, somehow, always does. Let that thought stay with you. Even in the darkest place, under the harshest laws, something finds a way out. Let it be enough. Let it carry you gently to sleep. Good night, traveller.